Okay, so bear with me at the beginning of this. It's going to be a little bit weird. I would like to talk about what these questions even mean. Okay, because this is some kind of mysterious stuff. If you look at this, I understand, what 5 squared means. You guys all know what 5 squared means, right? What does 5 squared mean? 5 squared means 5 times 5, right? Which in turn is 25. I even understand what 5 to the third means. It's just 5 times 5 times 5. 125. And I understand what 5 cubed over 5 squared means. I understand that. Because it just means I'm going to do 3 powers of 5, and then 2 powers of 5, and then ultimately divide. I even know a trick where I could have done this a little faster by doing 5 to the 3 minus 2, which gives us 5, right? Okay, but where exponents get interesting are where we deal with weird exponents, like what does 0 exponent mean? And what does 1.4 powers mean? Does this even have meaning? Okay, so I had a good discussion with my father about this a few weeks ago. So let's go back to this example. We know that 5 to the third over 5 squared is 5. There's 2 reasons. It's 125 over 25, but it's also 5 to the 3 minus 2, right? 5 to the first. So when we run into situations like 5 squared over 5 squared, there's 2 ways to tackle it. One is to look at it as 25 over 25, which of course is just 1. But a person who decides to use that subtraction trick would treat 5 squared over 5 squared as 5 to the 2 minus 2 and interpret it to mean 5 to the 0. But it's the same question as the previous line of work, right? The first person who did this problem got 25 over 25, which is 1. The second person got 5 to the 0, which is 1. So mathematicians saw this coming and they said, listen, we have to declare that 5 to the 0 is 1, otherwise we have 2 answers to the same problem. So by necessity, mathematicians said, look, this has to be 1. Otherwise, it doesn't make any sense.
So there's no proof?
It was defined this way, so it doesn't need proof. It's kind of like saying, why is a cat a 4-legged creature with whiskers? It's like, well, we made it that way. We just decided to call those cats. Okay? We decided to call this 1 because we didn't know what to do with it. You see? You can't have one person say, the answer is 1, and another person say, no, the answer is 5 to 0. Or if you ask that person, what's 5 to 0? They say, 0. No, it has to be 1. It has to be 1 because of this situation, see? Okay? And then it gets kind of interesting when you put more powers on the bottom than on the top. Like if you have 5 squared over 5 cubed, one person would interpret this as 25 over 125 and then reduce it to 1/5. Another person would say, no, it's 5 to the 2 minus 3. That's 5 to the minus 1. It's like, well, both people have to be right, of course. So we would then declare that 5 to the minus 1 must mean 1/5. We have to define it as such. So some of these rules of exponents were created out of necessity, for consistency's sake. So we have one answer to every question. Does everyone understand that? Okay? So then what does 5 to the half mean? That's a good question. Certainly doesn't mean the same thing as 5 cubed, right? 5 cubed means 5 times 5 times 5. You multiply 3 times, right? What does this mean? Multiply 5 by itself half a time? Doesn't mean anything. It's nonsense. Okay, so let me show you why this means rad 5. Why it has to be defined to mean rad 5. It's because if you think of 5 to the first, how many halves are in a whole? 2, right? Okay, so you would think of this as half plus a half. 5 to the half plus a half, right? Which can be split into 5 to the half times 5 to the half. Okay, so we're saying that 5 to the first is a product of 2 identical objects. 5 to the half and 5 to the half. But wait a minute. If 2 identical objects are multiplied to make 5, then what is A here in this situation? What is A? Okay, fine. We'll call this 5 equals A squared. What's A? Rad 5, right? Rad 5 is the only thing that when multiplied by itself produces 5 to the first. So in other words, that A must mean rad 5. And if A means rad 5, then 5½ means rad 5. See? That is really strange. That was really weird. I have no idea what just happened. Did you see that? It's on recording too. Okay. So listen, what I'm saying is these have to be rad 5s to make this statement true. And so I'm saying that rad 5 and 5½ must mean the same thing. Okay, so hopefully I've kind of convinced you of some of the basics and why they are true. And hopefully understand that some of these are just made up by mathematicians to keep everything nice and consistent. Okay, question?
If you have a squared equals 5, then wouldn't a equal plus or minus 5?
Yeah, but we only had, you mean plus or minus rad 5?
Yeah.
Yeah, this one was, I was working with the principal square root there, so we're not going to include the negative. Yeah, that's a good question. I think if you work that backwards, it wouldn't work with the negative case. Okay, what I'm trying to convince you of is that it's okay to have things like 5 to the 0. And it's okay to have things like 5 to the minus 1. It's even okay to have 5 to the 0.5. It just means half. Okay? So, I'd like to convince you that 2 to the 1.4 actually makes sense. It literally means 2 to the 14/10, which, as you know, means the 10th root of 2 to the 14. Okay? So it's very meaningful to write 2 to the 1.4. Makes perfect sense. It just means do 14 powers of 2, and then try to find the 10th root. I'm not saying I can do it in my head. I still need a calculator, but I understand it. Right? Maybe you can get the decimal on your calculator. Let's look at the next one. This would mean 2 to the 141/100ths. In other words, it literally means the 100th root of 2 to the 141. See? That's all. That's what it means. I can understand that. Big number. Try to find the 100th root. Right? Can someone tell me what this represents? Part C. What do you think that means? Raise your hand. One hand. What do you think it means, Rebecca?
It's 2 to the 1,414 to under the 100. That.
Okay, so it's
I don't know what to do with
14.
electronics,
No, it's okay. 1414 over what?
1,000.
Yeah, over 1,000. So it means
2 to the 14 power under the rad of 1,000.
right. So we pronounce this the 1,000th root of 2 to the 1,414th power. Yeah, exactly. Right. And the next one similarly would mean the 10,000th root of 2 to the 14,142. So these are all very meaningful. And here's where it gets a little bit hard to understand. 2 to the root 2. What does that mean?
2 to the 2 to the half. 2 to the 2 to the
It's 2 to the 2 to the half, but understand that this is 1.414. Someone give me some more digits on that. What is rad 2? I had you memorize it earlier in the year as simply 1.4, but obviously
1.414213.
and this doesn't end, right? So I can't write this as a radical the way I did A through D, because I don't know how to write 1.41423135 blah 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 as a fraction. I don't know how to do that. In fact, it cannot be done. So I cannot perform E the same way I performed A through D, but I'd like you to at least believe me that this still has meaning. The calculator can tell you what it is. What does that say, Jace? 2 point what? Right. Uh-huh. Lots of digits. It goes on forever. I don't really even expect it to have a pattern. So this has meaning. Okay? A through D is very obvious what it means now. The last one, we believe it has meaning, and we're going to just trust that it does, and I'll let your college teachers explain to you how it does have meaning. Okay? If you get that far in math, if you decide to take upper math classes. Okay, let's go on to the next part here. Laws of exponents. This isn't new. This is just saying things like, 5 squared times 5 to the third is 5 to the fifth. But if you do 5 squared and it's cubed, that's 5 to the sixth. You guys know these rules. And if you have like 5 over 7 and it's cubed, you can write that as 5 cubed over 7 cubed. No surprise there. If you have like 5 times 7 and it's quantity cubed, you can write that as 5 cubed times 7 cubed. If you have like 5 to the minus 3, that just means 1 over 5 cubed. This is obvious. 1 to any power is 1. And anything to the 0 power is 1. I tried to convince you of that earlier. Hopefully that, maybe for the first time you realized why 5 to the 0 is 1. The only exception is 0 to the 0. 0 to the 0 is not 1. Okay? But anything else to the 0 is 1. Okay, so I just wanted to remind you of those rules briefly so we can do some arithmetic with them if we need them. Okay, let's go on to the next part. Okay, anytime you see your base staying the same, see how my base is 2, 2, 2, 2, 2, but the power keeps changing, you can be sure that your teacher is teaching about exponential functions that day, okay? So that's what I'm teaching right now is exponential functions, the title of our section. An exponential function is when you have a constant base and a varying power, okay? For example, 2 to the x, I'm at the bottom here, I'll color code it, 3 to the x, 5 to the x, those are exponential functions, okay? You give me x, I'll tell you a y value, You say 3, I'll do 5 to the third, or whatever. You can also have fractional bases, like 1/3 to the x, or 1/2 to the x, or 1/5 to the x. In this class, we will steer away from negative bases. So we will not have problems like this, -2 to the x. The reason we will not study this is because it's too complicated. For example, if x is 0, I understand it. And if x is 1, I understand it. But if x is 1/2, it means the square root of -2, and it's not even real. Okay? So we will stay away from this problem here because the negative base causes all sorts of weird issues. Okay? And we will also stay away from base 0 because it's lame. It's just silly. What is y equals 0 to the x? Same thing as y equals what? 0. It's not a very interesting situation. And we'll also stay away from y equals 1 to the x, which is kind of equally trivial. 1 to the x is just 1, so this is just like y equals 1. These are not very interesting to us. But we will be interested in bases that are positive, real numbers, not 1. Okay? Like the ones I have below. 2 to the x, 3 to the x, 5 to the x, 1/2 to the x, 1/3 to the x, 1/5 to the x, even e to the x. Okay? Above, I tried to convince you that we can have any power we wish. Okay? Any power. Rad 2 even can be an exponent. Okay? If you can believe it. And so the domain of an exponential is all real numbers. All right, let's go to the next page and let's try graphing a simple exponential function 2 to the x. Okay, so when you run into a new function that you haven't graphed before, or maybe it's been a long time, just make a table. Right? Pick numbers. So I'm going to pick -3, -2, -1, 0, 1, 2, and 3. And if I plug these in, I get basically 2 to the -3, 2 to the -2, 2 to the -1, and so on. In other words, I'm going to get 1/8, 1/4, 1/2, 1, 2, 4, 8. How did I get these? I plugged in the x's into 2 to the x. Okay, and if you plot this, you get this. Okay? So at least try to get some of those points in there. 3, 8, 2, 4, 1, 2. Okay. you'll notice that the domain is really all real numbers. I can pick any x's I want when I'm making my table. Even root 2, or pi, is a power. Okay? As for the range, though, you'll notice that my answers are all different, right? But they share something. What do you notice about my range values? They're definitely all positive, right? In other words, you'll notice we never drew anything down in the lower quadrants. It seems like y is consistently a positive value. Even if you did like 2 to the negative 1,000th, it's still a positive number. It's technically 1 over 2 to the 1,000th, which is positive. It's just really, really small. Okay? Okay, so what I'm saying is the range is all real numbers greater than or equal, or greater than 0. So positive real numbers. This thing never goes lower than the x-axis. In fact, it never really touches the x-axis. So I'd like to draw an asymptote line here. And that line is required every time you draw an exponential for me. Okay? So every time you draw 2 to the x, draw that line there. Every time you draw 3 to the x, draw that line. E to the x, draw that line, please. Okay? Okay, and this is the graph of 2 to the x. I want it on a flashcard. I want the details that follow under here. In a moment, we'll go over the details of this graph. I want those on the card, just like we made flashcards for all the other graphs. This one you add to your list of memorized ones. Okay? I also am going to have you do 3 to the x, which is basically a little steeper. So let me draw 2 to the x and 3 to the x together for you, just so you can see them together. If 2 to the x looks like this, 3 to the x looks like this, it's steeper. Everywhere, steeper. Okay? And e to the x is the third one you have to know for this class. It's between them. And the reason for that is e is a number right around 2.718. Okay, so the graph is going to fall right in between 2 to the x and 3 to the x. You kind of need to know these 3 graphs. Okay? And you'll need a note card for each one. Yeah?
For the graphs, for all 3 of those, is the slope the same, just like the hero line?
The only thing they share is general structure, shape, and they share the same y-intercept. They all contain the point 0, 1. Other than that, they don't touch anywhere else.
Like the slope, because like 3 to the x, it looks like 2 to the x, but it's just like kind of like angled up. Like,
It's steeper.
like angled. I don't know how to explain.
I know, it's hard to explain. You basically have on the right side, the red is above the black, which is above the blue, okay? And that's because 3 grows the fastest when you're out in the positive power range. Like 3 to the first is bigger than e to the first, and it's bigger than 2 to the first. So these points of the 3 at x equals 1, 3 to the first is the highest. If you come into the fraction, or into the negative realm, they all kind of trade roles, because if you do 3 to the minus 1, that's a third, but 2 to the minus 1 is a half, which is bigger. So you can see that the blue curve is actually above the red. See? But just keep in mind that they go in order 2e3 in terms of steepness, and then just kind of sketch the 2 to the x and the 3 to the x, and then try to squeeze the e to the x in between them. I don't need perfection on these. You can always use a calculator or a table to get perfection, but you need to know the general shape. And I said you need to draw this line every time. The horizontal asymptote. Very important to me as a calculus teacher. So let's go to the little properties of this graph. Okay? I hope I answered your question, Catherine. If not, maybe we can talk later. Let's go to the properties. So what do we notice? The domain is all real numbers. The range is the set of all positive real numbers. There is no x-intercept anywhere. But the y-intercept is always 1. So whether you're graphing 2 to the x, or 3 to the x, or e to the x, they all have the same y-intercept, 1. Okay? But there's no x-intercept. We can see that the x-axis is a horizontal asymptote, and I've asked you a million times today, you're going to have to draw that in, okay, every time. You'll see that these graphs are strictly increasing. They're always on the up. They're rising, 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 rising forever. In fact, they're called exponential growth graphs. They grow. That's all they do. They never shrink. They never fall. They go up forever. So you can put a little arrowhead on here to remind yourself these guys always grow. But this also has an important implication to us. It means that they're going to be one-to-one. Okay? They're all going to be one-to-one. They pass the horizontal line test with flying colors. You can draw the horizontal lines and they'll pass every time. That's important. That means there's an inverse. Okay? Graph of f always contains the point 0, 1. Remember I said the y-intercept was 1? And they always contain the point 1a. Okay? For example, the blue graph contains the point 0, 1 and the point 1, 2. And the black graph contains the point 0, 1 and 1e. And the red graph contains the point 0, 1 and 1, 3. See? So it always contains one comma base. One comma base will be on the graph. The graph is always continuous, means unbroken, can be drawn without lifting your pen, and differentiable. Can someone remind us what that word means? It says right there, but no sharp turns, right? Okay. Now what happens if you're dealing with a graph like 1/3 to the x? In other words, what happens if a is between 0 and 1? So examples would include 1/3 to the x, or 1/2 to the x, or 1/e to the x, which is kind of weird. What would you do with those? Listen, I don't want to make a big deal of these, because these three can be rewritten like this. Watch. This can be written as 3 to the minus 1 to the x. This can be written as 2 to the minus 1 to the x. And this can be written as e to the minus 1 to the x. In other words, these are just 3 to the minus x, 2 to the minus x, and e to the minus x, which are just reflections over the y-axis. Remember the negative x causes the graph to reflect over the y-axis? I'm not going to make a big deal of this. That's just a basic transformation. Okay? So I'll write down a few facts, but honestly, they're just reflections over the y-axis. Okay, so I'll write that in here. I'm saying that these are reflections of y equals 3 to the x, y equals 2 to the x, and y equals e to the x over the y-axis. No big deal. Okay, so I believe the domain would still be all real numbers. Still. The range is still all positive real numbers. That hasn't changed. There's still no x-intercept. The y-intercept is still 1. Just because you flip it backwards doesn't change the y-intercept. The x-axis is still a horizontal asymptote. Okay, f is now decreasing. That's true. That's a little different. Your graphs will now look like this. You know, 1/2 to the x. It'll be falling instead of rising because it's reversed, but it's still 1-to-1, right? So we'll fill that blank. The graph still contains the point 0, 1 and 1a. It's just a is now a fraction. The graph is still continuous. The graph is still differentiable. The only thing that happened between my first set of properties and my second set of properties is I did fraction basis, and that just means reversed. It's not a big deal. It's just literally flipped over the y-axis. Now, if I had not taught you transformations, then I would have spent, a good 20 minutes on that. Okay, let's go on now and talk about just graphing something. Like, how would you graph this function? Well, if you want to, you can make a table, but that's kind of cheating. You're supposed to use transformations, and you're supposed to kind of know that the parent graph here is 2 to the x. So by the end of the week, you'll definitely have this graph perfectly memorized, okay? We already kind of drew it once. I'll draw it again. This is my parent function. And some things have been done to it. So, for example, I see a couple negatives, right? There's a -3 going on. What's happened? Okay, so we can see there's a negative on the x up in the power there. So this is going to flip the graph over the y-axis. So let's take care of that now. And let's flip this thing over the y-axis. Okay, let me try and get it a little bit more accurate there. There we go. That's not a very good drawing. It's not my final drawing, though. This is y equals 2 to the minus x. Okay, the dashed one. And then there's another negative in the front, in front of the 2 to the x. So what does that do to the graph? Inverts it, right? Flips it upside down. Okay, so we've got to flip it over the x-axis now. So this is y equals -2 to the minus x. And then somebody went ahead and subtracted 3 here. See that? What does that do to the graph? We should know that by now. Shifts it down 3, right. So this is just a translate down 3 type thing. So I think what happens here is, first of all, the asymptote drops. Okay, the asymptote was originally on the x-axis, but that has dropped down 3 spaces. So now it's right here, see? This is my horizontal asymptote at y equals -3. So that's been moved. By the way, asymptotes always move with the graph, okay? And now I've got to drop all my points by 3 spaces. Okay, so it's going to look like this. And I don't need you to label all the points, okay? I need you to know the basic structure. You're going to be using graph paper for the 5 problems that you're asked to do, and I'd like them to be tidy, but you don't actually have to write the coordinates out, especially some of these weird ones that are in between -3 and -4. Those are awkward to work with, okay? But some of them are whole numbers. You could do those, right? Like the integer ones. Like there's a point there at -3, -11. That's not hard to find. Okay, so if someone asks you to graph a exponential function, they're talking about 2 to the x, 3 to the x, e to the x, that sort of thing. Okay? And they have these basic shapes. If somebody asks you to graph the exponential function, they're talking about e to the x. Okay? So let's go down here and fill in this blank. The natural base, e, you've heard of it in your science classes, e is about 2.71828. And there's a calculus definition of it. We don't need it right now. But this is the exponential function. All right? So I'm telling you, if someone says, hey, what is the exponential function? You're supposed to say e to the x. If they say, what is an exponential function? You can say 2 to the x, 3 to the x, 5 to the x, or e to the x. But the exponential function, he's e to the x. The most important one of all, actually, to most scientists and mathematicians. Also, if someone says the logarithm, they're talking about ln, not log. Okay? E is huge in calculus. We don't even use other bases hardly ever. But for now, just know that e is about 2.7. And I don't need a real detailed sketch of this one. But know that it passes through 0, 1, like all the others. It passes through 1 comma base, which is going to be e this time. And that's about 1 comma 2.7-ish. And then, of course, it's going to pass through 2e squared and 3e cubed and -1, 1 over e, and -2, 1 over e squared, and so forth. none of which I'm willing to plot, except maybe I'll plot 2 comma e squared. I think it's between 7 and 8. So this one, again, I don't need a lot of detail, just so you know it's between 2 to the x and 3 to the x graphically, as I showed you earlier. Okay, maybe on your note card you can have 3 or 4 decent labeled points. Okay, and then the last thing you need to know for this section is something I don't even need to teach you again. I'll just do really quickly go through 3 examples. You've done it so many times, and I'm pretty sure you're really good at it. Take a look at the next page. These are those problems where you're trying to solve for x. And so what you can do is try to get the bases the same on either side. So you'll notice that 81 is just 9 times 9, which is 3 times 3 times 3 times 3, right? So you could write 81 as 3 to the 4th, right? And then once you have the bases the same, you can cross them out. So you can write this as x plus 1 equals 4. So what's the answer for x on this problem? 3. How many of you remember doing this in Algebra 2 class? This is something you were drilled heavily on. I'll bet your test had like 15 of these questions on it. Maybe. Okay? The next one, same idea. You've got a 4 base and you've got a 2 base, but you'd like them both to be the same. I find it easier to write a 4 as 2 squared. So I'm going to write the 4 as 2 to the 2nd. And this gives me permission to cross out the 2's. So what's my resulting equation?
2 to the x power squared.
It's 2x squared equals x, right? So just take what survives the cancel there. There it is. 2x squared equals x. And be careful solving it. Just bring everything to one side carefully and factor out an x. Don't try to cancel out the x or whatever. So go like that. Pull out an x. Okay, it looks like we've got x equals 0 and x equals a half. Really easy to check your work. You can just plug these 2 numbers, one at a time, into the original problem, and you come out with a true statement. 1 equals 1, or root 2 equals root 2. Okay, let's go on to the next and last example of the day. This one looks awful. It's the right side's fault. Left side's fine. Let's see if we can get that right side cleaned up a little bit. By the way, don't cross out the e quite yet. Some people get cancel happy and they're like, ooh, goodbye e. You can't do that, okay? Let's get the right side to look like e to the something. Okay, so first thing I notice is this is just e to the 2x. And this is just e to the minus 3. So that helps. And then I can put those 2 together as e to the 2x minus 3.
You're not getting the squared on the left.
I forgot the square on my left side there. Thank you. E to the minus x squared equals e to the 2x minus 3, because you're supposed to add the powers there. And now you can cross out your e. So just don't do it too soon. You get 1 hash mark per side, okay? Don't cross out a bunch of e's. Just 1 on each side. And then this needs to be solved carefully. How about bring everything to the right and factor? Okay? And that's how you do it. You can also kind of cheat on these too. You can actually graph y1 equals e to the minus x squared, and it looks like this, like that. And then you can graph y2 equals e to the 2x minus 3, which is going to look something like this. And then they cross. You can see where they cross using your intersect button. They cross at -3 and 1. Okay, that's the answers we got here. What is the intersection point? This is a very educational thing to do, but it doesn't substitute for doing the work. It's actually not that much faster. All right, so I know I crammed that lesson in, but I kind of had to because I was getting behind the other teachers. So now I'm kind of caught up. I can slow down a bit.